So we spend a lot of time talking about voltaic cells where we use a chemical reaction in order to produce a voltage, which then results in a current, which we could use to make batteries, run things, and so on and so forth. So we use a spontaneous process in order to convert chemical energy into electrical energy. Now what we're going to do is we're going to look at a different type of cell. And in this cell, it's called an electrolytic cell. And in this cell, what we do is we put energy into it. So we have to apply a voltage to it. And what we're going to do is we're going to make a non-spontaneous process occur by adding energy to our system. So to see how this is done in an electrolytic cell. So say that I want to get sodium and chlorine from sodium chloride salt. So what I'll do is I'll have maybe this vat, okay? And this vat will have molten sodium chloride in it. So that means that I'm going to have sodium ions around. Okay, I guess that'll be liquid. And I'm going to have chloride ions going around. Okay. And I want to do the following. I want to have the sodium gain an electron and turn into sodium metal. And then I want the chlorine to lose electrons and turn into chlorine gas. Okay. So what I need to do is I need to hook this up to some power source. Okay. And so I'm going to have two electrodes. And on this one, okay, this is going to be my negative electrode. Okay, so my negative electrode is going to get on here. And there'll be these electrons on it. And what I'm going to do at this electrode is I'm going to force this reaction to occur. Okay. So I'm going to force that reaction to occur at this electrode. And because this is a reduction, this is going to be my cathode. Okay, so this is consistent with voltaic cells. Reduction always occurs at the cathode, but my electrons are running down this side. Okay. And then my positive will be hooked up over here to some other electrode. Okay, and so this one's going to take electrons from it. And so what's going to happen on this side is I'm going to force this reaction to go. I'm going to say two chlorides go to form chlorine gas plus two electrons. And I need to put energy into this. I need energy. So, sorry, this is my anode. Okay, so this is where my oxidation is occurring. So I need to put energy into it. I need to put energy. I need to shove electrons on the sodium. And I need to take electrons. I need to rip electrons away from these chloride ions. And so the question is, okay, well, fine. How much voltage do you need to do this? Well, the net reaction that I'm going for is essentially sodium plus two chloride ions goes to sodium plus chlorine gas. That's what I want. And I can calculate the cell potential of this. So what you can do is you can say, okay, this reduction potential for sodium is going to be negative 2.71 volts. And this oxidation potential for the chloride, okay, so I'm going to call this the oxidation potential. If you look at the reduction potential around backwards, it's going to be negative.
Okay.
So this oxidation potential is going to be negative 1.36 because the reduction potential, this reduction potential is going to be positive 1.36. So when I add these two together, I'm going to get an E cell of negative 4.07 volts. So what this means is that in order to accomplish this, I need to apply 4.07 volts. But if I do that, then I kind of climb the hill that I need, the energy hill that I need, and this electrolysis will occur. And it's called electrolysis, that you can see, because I'm breaking apart the salt. I'm lysing it, breaking it apart. I'm using electricity. Okay, so that's the basic. That's the basics of just a basic electrolytic cell. Interesting fact. Notice that in our voltaic cell, the cathode was my positive electrode and my anode was my negative, and those signs have switched. It's a small point, but just thought I'd mention it. Okay, so kind of moving on here, some of the things that we do with this with the electrolytic cell. So what we do, or one of the things that we do, is we can electroplate. So when we electroplate using, so I'm going to try to pick out a color here. Excuse y'all. So when we electroplate, what we can do is we're going to have this vat here, right? By the way, that's another difference. Notice that because the reaction is non-spontaneous, I don't need to separate the products, the reactants from each other. I can do this all in one vat because they're not going to react together anyway until I put energy into it. And then once I do, I can determine the direction of the electrons. I can determine what's going to be oxidized, what's going to be reduced. So say that I have a piece of metal and I want this piece of metal to be plated, okay? And chrome plating is, very popular. So what I can do is I can make the solution. I can put chrome 3 plus ions in this solution. And then on this side, I'll put, a piece of chromium maybe. And this is the metal to be plated. It doesn't matter what this metal is. So metal to be plated. And let's separate this words a little bit. So metal to be plated. Okay, so I want to plate this metal with chromium. So on this side, what I want is I want the chromium 3 plus ions to be reduced to chromium metal on the surface of this. Okay, then on this side, I'll replenish that by having the chromium metal going to form chromium 3 plus ions and losing 3 electrons in the process. So when I set up my power source, what I want to do is I want to hook it up, and I want this side to be negative. So what I want to plate, I hook up to the negative side, and then the other side I'm going to hook up to my positive. Okay, so this is going to remove the electrons, and then this will put the electrons onto this piece of metal, and then the chromium will be reduced on it. Okay, so I can have my cathode over here, my reduction on that side. Okay, now a fun fact, because if you look at the net reaction of this, I'm taking chromium metal, okay, taking this chromium metal, and I'm converting it. Let's see, let's make sure I get this right. So chromium metal plus chromium 3 plus ions. Okay, so these are my reactants. The chromium metal, the chromium 3 plus ions over here, going to chromium 3 plus ions. So this is going to form the chromium 3 plus ions, plus chromium metal on this side. Essentially, I'm just transferring atoms of chromium from one side to the other. And it turns out that this has a cell potential of 0 volts. So really, any voltage works for this. It doesn't matter what voltage you have, we'll be able to do electroplating. Okay, now we'll talk in class about the effect that voltage and current does have on the rate of electroplating. The process itself will work no matter what voltage you have. Okay, and finally, and this is a problem that comes up a lot in AP chemistry. And so what this problem asks is, you have this vat, okay, and you'll have this vat of aqueous solution of some ionic compound. So for this example, we're going to look at aqueous potassium bromide. And so this is water, and we'll apply a voltage to this. So maybe negative, positive, and we'll have our electrodes on each side. Okay. And so on this side, okay, this is our cathode. And on our cathode, something's going to be reduced. And when we think about what we have in our, I'll get this right yet. When we think about what we have in our solution, we have potassium ions, we have bromide ions, and we have water. Okay, now, water can be oxidized and reduced just as well as these ions can. So what we need to decide is what's going to happen at each of these electrodes. So at the cathode, we have two possibilities of what could be reduced. We have the potassium plus that could be reduced to potassium metal. Okay, that's a possibility. Or what we have is a competing reaction. We have water, and if you look at the reduction potential for water, you'll see that water can gain 2 electrons to form hydrogen gas and hydroxide. So if you had phenolphthalein here, you would actually just turn that kind of pink. All right. And so what you do is you say, okay, I could reduce this or I could reduce this. This reduction potential for potassium is going to be negative 2.92 volts. And this reduction potential for water is going to be negative 3 volts. So one of these is going to be reduced. And you can see from these numbers, it's going to be easier to reduce water than it is to reduce the potassium. In fact, potassium reacts with water, and this shows you why. So because of that, what's going to happen is that on this side, we're going to have this reaction occur. We're going to have the water be reduced. So on your cathode side, when you have an aqueous solution, you compare the reduction of water, this equation, with the reduction of the positive ion in your solution, and you see which one's more positive. Whichever one's more positive, that's going to be reduced. Okay, so we have little bubbles of hydrogen being formed on this side. Then on the other side, what could be oxidized, we could have the bromine be oxidized, the bromide ions rather, be oxidized. Okay, or we could have water be oxidized. And when water gets oxidized, it follows this reaction. So water will be oxidized to oxygen gas plus H plus ions plus that. And so if you look at the reduction potentials of these reverse reactions, okay, and then essentially reverse them, you will get the oxidation potential. So the oxidation potential for bromine is 1.09 volts. And for water, the oxidation potential is negative 1.23 volts. And so now we see that when we compare these two, it's going to be easier to oxidize the bromide ion than it will be to oxidize water. So on this side, we would see bromine being formed. Okay, so orange, like you'll see like orange bromine being formed on this side. Okay, so that's how we analyze the products of an electrolytic cell when we have an aqueous solution. Okay, we compare the reduction of water with the positive ion that can be reduced to see which one's more positive. For the anode side, we compare the oxidation water with the negative ion that can be reduced, and whichever one's more positive, that's the one that's going to occur. So I'll work on this more in class, guys, and I have some sample problems for you, and if you have any questions, please let me know.